All right, this is question number 1 from the 1999 AP Calculus AB exam. It's a motion question, it's a calculator question, and they've got a particle moving along the y-axis with this velocity of t times the sine of t squared for t greater than or equal to 0. And the first thing it asks us is in which direction, up or down, is the particle moving at t equals 1.5? Well, all we have to do is find v of 1.5. If it's positive, the particle is moving up, and if it's negative, the particle is moving down. And so we'll just use our calculator since this is a calculator question. We just want to find out what is 1.5 times the sine of 1.5 squared. And that's 1.167. You don't actually need the value here of it, right? But we'll write it. It's approximately 1.167, which is greater than 0. And so v of 1.5 is greater than 0. So the particle is moving up. And they gave you just 1 point here for part A, for your answer with a valid reason. In part B, it says find the acceleration of the particle at t equals 1.5. And then they ask a question that is a little off from what they lately have been asking, which is the velocity increasing at t equals 1.5? So first, to find the acceleration at 1.5, since this is a calculator question, right, we can just say a of 1.5 is v prime of 1.5. And our calculator will approximate that value for us. Now, you could take the derivative by hand using the product rule, but it's a lot easier to just go in and hit math, option number 8, and you can just hit the H. You don't have to scroll down to it. And now we want a derivative with respect to x of our function. We're going to write it in terms of x, so it's x times the sine of x squared. And we just want to know what that is at t equals 1.5. Well, it's negative 2.049 if we round to 3 decimals. So negative 2.049. So that's our value of the acceleration. And since the acceleration is negative, the velocity is going to be decreasing. So we'll say, no, the velocity is not increasing, because it asks, is it increasing? So the answer is going to be no, it is not increasing at t equals 1.5 because v prime of 1.5 is less than 0. And you get 2 points for that, one for the value, which they did ask you for, and one for the answer with the reason. In part C, it says, given that y of t is the position of the particle at t, and that y of 0 is 3, find y of 2. Well, to find y of 2 here, we just need to recognize that if we integrate the velocity from 0 to 2, that should tell us the displacement of the particle, or its change in position, between 0 and 2. So that should tell us what y of 2 minus y of 0 is. Well, if we want y of 2, because that's what it says to find, just add y of 0 over to the other side of this equation. We want y of 2, which is going to be y of 0 plus the integral from 0 to 2 of v of t dt. You don't actually have to try and integrate that, which is not so bad to do. It's just a basic u sub. We're just going to use our calculator here. Since y of 0 is 3, we'll just do 3 plus, and then our integral, which is math, and option number 9 for the integral from 0 up to 2. And we're going to just put in our v of t function, which was x sine of x squared. We'll put our dx out here. Our calculator will do the work and give us 3.827. So we'll just say it's about 3.827. They'll give you 3 points for this. They're going to give you 1 point here just for having an integral from 0 to 2 of v of t, or even an integral of v of t, an indefinite integral. 1 point for using the initial condition here or if you did it by hand, 1 point for having the plus c attached to the correct integral, and 1 point for the final answer. And of course, if your final answer was in exact terms, that would have been okay if you did it all by hand, but much quicker and easier to use the calculator. And in part D, it wants the total distance traveled by this particle on the interval from 0 to 2. Again, it's a calculator question, and total distance traveled is an integral of speed, which is the absolute value of the velocity. So all we have to do here is integrate the absolute value of the velocity from 0 to 2. And again, since this is a calculator question, you're just going to do this on your calculator. You're going to hit math, option number 9. And I didn't scroll down that time, but you can just hit the 9. We're going to integrate from 0 to 2. To get absolute value, we hit math. We go over to the second column, option number 1. We'll put in our function again, x times the sine of x squared. We'll say dx out at the end, and we'll get our final answer of 1.173. And you'll get 3 points here for this. Your scoring guidelines are going to show how to do it by hand also, but there's no need to do it by hand by finding when the velocity changes signs, because it's a calculator question. So you'd be getting 2 probably here for this setup and 1 for your final answer. And that is the end of this motion FRQ, question number 1 from the 1999 AP Calculus AB exam. All right, this is question number 2 from the 2000 AP Calculus AB exam. We have 2 runners running on a straight racetrack from t equals 0 to 10 seconds. And the graph above, which is 2 line segments, shows the velocity in meters per second of runner A. And the velocity in meters per second of runner B is given by this function v of t, which is 24t over 2t plus 3. We want to find the velocity of runner A and B at t equals 2. So, well, for runner A, the velocity is just going to be whatever this value is right here. And so we know that this is a linear function. And so if we are going from 0, 0 to the point 3, 10, we can just find the slope there. Right? The slope is going to be 10 minus 0 over 3 minus 0, or 10/3. Well, we're going to go up 10/3 every time we go over 1. So the velocity of A at 2 ought to be 10/3 times 2, which is 20/3. And we want units here, so the velocity, they've already even told us, it's just meters per second, so you better not miss meters per second since they tell you both of them are in meters per second. And then for runner B, the velocity of runner B at 2, well, we just need to plug in 2 to this. Well, 24 times 2 is 48, and 2 times 2 is 4, plus 3 is 7. So that one is 48/7 meters per second. And they gave you 2 points for that. So 1 point for runner A and 1 point for runner B. In part B, we want to find the acceleration of both runners at t equals 2. Well, the acceleration is just the derivative of the velocity, right? So we're going to say v sub a of, v sub a prime of 2 should be a sub a of 2. Well, we already know that the derivative, or the slope, of this velocity function is just 10 over 3. So we can just say this is 10/3 meters per second squared. Right? We already did the work to find that value in part A. In part B here, when we want runner B, well, we're just going to take the derivative v prime of 2 should be a of 2. Okay? And so runner B, and we should probably note that's runner A over here, and runner B here. Well, we can use the quotient rule to take that derivative, but since this is a calculator question, I'm just going to use my graphing calculator here. I'm going to hit math, and I'm going to go down to option number 8, and I'm going to say I want the derivative of that function, which was 24. I'm going to do actually alpha x to get a nice fraction. The original function was 24x over 2x plus 3, and we wanted to evaluate this at x equals 2, and so that's going to give us 1.469, and we'll just say 1.469 meters per second squared. And that was worth 2 points as well, one for each of their accelerations. In part C, which is the last part of our question here, it wants us to know the total distance run by A and B on those 10 seconds. Well, since the first runner's velocity is always positive, we know that his total distance traveled is just the area underneath this curve, right? So for runner A, I'll do this up here. Runner A, it should just be whatever this area is, which this is a trapezoid with a base of 10 across the bottom and 7 across the top. So that's going to be 10 plus 7 divided by 2, right? The average of the bases times the height of this function, which is, we're going up to 10 here. So times 10. And, well, you know, I can just do the 10 over the 2 here. So this is 10 plus 7, or 17, times 5. And 17 times 5 is 85 meters. So he ran 85 meters. Runner A ran 85 meters in those 10 seconds. And then for runner B, now we could go through and check and see if runner B's velocity is always positive. But just to be careful about this, right, for runner B, we can always, and there's no reason to be going backwards, but we can always just integrate for total distance the absolute value of the velocity. And so you should always just do that just to be safe. And so if we do this, we'll go into our graphing calculator with math. We'll go down to option number 9. We're going to integrate from 0 to 10. And to get absolute value, we're going to hit math. We're going to go over to the second column and pick option 1 for absolute value. And then we'll just put our 24x over 2x plus 3 function. And again, I'm going to hit alpha x and put in 24x over 2x plus 3 dx, which gives us 83.336 meters. And we get 4 total points for that. 1 for the correct method on A and the answer on A. 1 for the method on B and the answer on B. And then we get a final point for having the appropriate units from parts A, B, and C. You had to have the right units in all of them, and that was worth 1 more point. And that is the end of this motion FRQ, question number 2 from the 2000 AP Calculus AB exam. All right, this is question number 3 from the 2001 AP Calculus AB exam. It's a motion question, and back in 2001, they had 3 calculator questions. So question number 3 here from this exam is still a calculator question. And we got a car traveling on a straight road with a velocity of 55 feet per second at t equals 0. So we have an initial condition for our velocity. And from 0 to 18, we have the acceleration given by this piecewise linear function. We want to know, is the velocity of the car increasing at t equals 2 seconds? Well, our velocity function, its derivative is the acceleration, right? So we can determine if a function is increasing or decreasing by looking at its derivative at that point. So v prime of 2, which is a of 2, is just equal to 15. Well, 15 is greater than 0, so we can say the acceleration at t equals 2 is positive, So the velocity is increasing. And they just gave you 1 point for that. In part B, they want to know on what time interval 0 to 18 other than t equals 0 is the velocity of the car 55 feet per second. And so in order to figure out that, the only way to figure out what the velocity is at any given point is to integrate different pieces of this function to see if it ever equals 55 again, right? So the integral of acceleration should be the velocity, right? And it should be the change in the velocity. And so clearly on all of these intervals, when my velocity or my acceleration is positive, right, my integral there is going to be a positive value. And therefore, that means that the velocity is increasing. So it's certainly not going to be 55 on any of those time intervals. But somewhere along here, on this section down here, it would seem that there's going to be a place where the velocity is back to 55, because somewhere along here between 6 and 16, those negative areas under the curve are going to cancel out with the positive areas underneath the curve. And so first, let's figure out what the integral from 0 to 6 of v of t is, and then we can find where it's got that same opposite value on the rest of it. So from 0 to 6, that's just a trapezoid with a base down here of 6 and a base up here of 2. We'll divide that by 2 and multiply by the height of 15. So looks like that comes out to be 60, right? 6 plus 2 is 8. 8 divided by 2 is 4, and 4 times 15 is 60. So I need to figure out down here where it's equal to negative 60. Well, conveniently, this is going down linearly, so it's the same rate there. And so this triangular portion right here should be the same as this triangular portion right here. And then we just need to go 2 more units, right? So let's test to make sure. If we do the integral from 6 to 12 of v of t dt, we're going to end up getting, well, we're going to have we're going to have 6 and 2 again, right, as our 2 bases. And this time we're going to be multiplying, though, by negative 15. Right? And so we get negative 60. And so we can say the velocity is 55 at t equals 12, because the integral from 0 to 12 of, not v of t, of a of t is equal to 0. And we would note probably here too that our velocity is going to be less after on this extra trapezoidal piece here, and that is going to be more than what we have back above, because these two here and here are going to match up. So we still have this amount extra that we went below 55. So it's not going to happen any other times other than at t equals 12. You get 2 points for that, 1 for 12 and 1 for the reason that that integral of acceleration is equal to 0. All right, in part C, it wants to know what is the car's absolute maximum velocity. It also wants to know where it occurs. And so, well, the velocity is increasing whenever the acceleration is positive, which is all from 0 to 6. And then we already indicated that the integral from 6 to 18 is going to be negative, right? So we could say since since a of t greater than 0 on 0 to 6, and the integral from 6 to 18 of a of t dt is less than 0, we can be guaranteed that the absolute max is at t equals 6. And in the previous part of the problem, we already found the integral from 0 to 6, right? And that maximum is just going to be 55, what we started at, plus the integral from 0 to 6. And I keep writing v of t here, but it's a of t, because most of these, they give you a velocity function. So a of t dt. So 55 plus that integral from 0 to 6, which we, as we said before, was equal to 60. And so that gives us 115 feet per second. And they gave you 4 points for that answer. 1 point for saying t equals 6. 1 point for some statement about t equals 18 there. And then 1 for eliminating t equals 18, like with this integral statement. And then 1 for the actual answer of 115 feet per second. And here in part D, we want to know at what times in the interval is the velocity equal to 0. Well, it could only equal 0 after we've increased to this maximum, because we started at 55 here at t equals 0, and we increased right here, our velocity was 115. So first thing we'll check is just what happens between 6 and 16. If the integral from 6 to 16 of a of t is not at least a negative 115, right, that would be what would drop us down to 0, then we know it doesn't. But if there is at least negative 115, then we're going to have to find out exactly where it does equal negative 115. So let's see what the integral from 6 to 16 of a of t dt is. And so that's just a trapezoid. From 6 to 16 is a base of 10. And then the base down here from 10 to 14 is going to be 4. So we have 10 plus 4 over 2. Right, the average of the bases times the height of negative 15. And so, well, 10 and 4, is 14. 14 divided by 2 is 7. And then 7 times negative 15 is negative 105. And so that tells us that the absolute minimum velocity is going to be whatever we were at t equals 6, which is 115, minus the amount that we lost here, which was 105, and I wrote 155 instead of 115, so we'll go back and fix that. 115 minus the amount we lost, which was 105. So the minimum velocity is 10. Well, therefore, v never equals 0. And we know it can't be after that, because after that we're increasing again because our acceleration is positive. They gave you 2 points, 1 for saying never, and 1 for the reason, which is this work up here that we showed where the minimum velocity had to be more than 0. And that's the end of this motion FRQ, which was question number 3 from the 2001 AP Calculus AB exam. All right, this is question number 3 from the 2002 AP Calculus AB exam. It's a motion question. And back then, question number 3 was a calculator question, so this is still a calculator question. And we've got an object moving along the x-axis with an initial position of 2 at t equals 0. And we have a velocity function for it that's valid for t greater than or equal to 0 of the sine of pi over 3 times t. We want to know the acceleration of the object at t equals 4. This is a calculator question, so you can just have your calculator take the derivative of that, or you can just take the derivative of it yourself, which should be pretty straightforward, right? A of t is v prime of t, and, well, the derivative of sine of something is cosine of that thing, times the derivative of that thing being pi over 3, right? That's the chain rule. So we have pi over 3 cosine pi over 3t, and so a of 4 is just pi over 3 times the cosine of 4 pi over 3, and the cosine of 4 pi over 3 is negative 1/2, so we have pi over 3 times negative 1/2, which is negative pi over 6. So you could do that to get your 1 point for that part just by hand. If you prefer to, you can just do your calculator there. Just go to your calculator, hit math, option number 8, and you're going to say d dx of your function that we had was the sine of pi over 3 times t, or we'll do pi over 3 times x. I like to do alpha x to get a nice fraction, so we have pi over 3 times x. Of course, you can put the x in the numerator also. And we wanted this at x equals 4. So, that gives you negative 0.5235987775, which if you put in negative pi over 6, you can see that those are the same thing there. Right? So either way you choose to do it, just make sure you round to 3 or more decimals if you do it on your calculator. So 1 point there for part A. In part B, it asks us to consider 2 statements. One is that from 3 to 4.5, the velocity is decreasing. And 2, from 3 to 4.5, the speed is increasing. And it asks us, are either or both of these statements correct? Well, to figure out if number 1 is correct, to see if the velocity is decreasing, we need to know about the acceleration, right? If the acceleration is negative, right, then the velocity would be decreasing. Velocity decreases if acceleration is less than 0. So let's first figure that out. Well, we know the acceleration function. We just found it, right? So a of t, which is pi over 3 cosine pi over 3t. We just did that in the previous part. We just took that derivative. Now, if we're not sure about what's going on with that between 3 and 4.5, our graphing calculator is a good way to go there. We can just, in our graphing calculator, we can do the alpha x to get this nice fraction. We can put pi over 3 cosine of pi over 3 x. And we can just graph that on the window that we're interested in. So we'll hit window. And the x minimum is going to be 3. And our x maximum is 4.5 because that's the interval it's talking about. And I'll just hit graph from there. And we can see that, well, it sure looks like the acceleration is negative on that entire interval. And since the acceleration is negative, then it must be true that the velocity is decreasing. So we'll say this is less than 0 on 3 to t to 4.5. So statement 1 is correct. And that's good enough reason that a of t is less than 0 on that interval. And then for statement 2, if the speed is increasing, well, speed has to do with the absolute value of the velocity, or it has to do with the velocity and the acceleration having the same sign on that interval. So if I just go in here now and graph on my y equals screen here, sine of pi over 3 times x, which is our velocity function, when I graph that, we can see that that is also negative on that entire interval. Right? And so we can then go back here and say statement 2 is correct because a of t less than 0 and v of t less than 0 on that interval. And therefore, statement 2 is also correct. They give you 3 points here for this. 1 for the whole stuff with statement 1. The second one was for saying statement 2 is correct. And the third point was for your reason that a of t and v of t were less than 0. All right, in part C, it asks us for the total distance traveled. Now, this should be a very easy question on a calculator motion problem. Total distance traveled is always an integral of the speed, right? It's the definite integral on this interval from 0 to 4 of the speed. Well, speed is the absolute value of the velocity. And so all we have to do here is just use our calculator to integrate the absolute value of the velocity from 0 to 4. So I'm just going to go back here to my graphing calculator. We'll hit second quit to go out of that. We'll do math and option number 9 down here, FNINT. And we're going to integrate from 0 to 4. And it has to be the absolute value of our velocity. So absolute value is in the math window, just underneath alpha. It's the second column, option number 1. And now our velocity function was just, once again, sine of pi over 3 times x. And we'll put our dx out in the end there. And we end up getting 2.387. And that's all you have to do. You get 3 points for that. 1 for having the limits and the integral there correct. And let's see. Well, actually, I think, and then 1 for having the absolute value. So I think 1 for the limits, 1 for the integral, and 1 for the final answer there. That's it for part C. In part D, it asks us for the position of the particle at t equals 4. Well, we know that an integral of velocity gives us displacement. So I can figure out exactly how far the particle goes from, let's say, from its initial position of 0 to its new position of 4 by integrating the velocity on the interval from 0 to 4. Right? That will give me the position of this at 4 minus the position at 0. Right? It just tells us the displacement on that interval. Well, if I want to know where it is at 4, that's what the question is asking. What's the position at 4? Just add this x of 0 over. We get x of 0, which in our case is 2, plus the integral from 0 to 4 of the sine of pi over 3t dt. And I forgot my dt up there, so we'll add it in. And so all we have to do is just plug that into our graphing calculator and get an answer. So we'll go back here. Our initial position was that it was at 2, so it's 2 plus, and then math, option number 9. And again, you could just hit the 9. You don't have to scroll down to it. Our integral is from 0 to 4, and it's just that sine of our pi over 3 times t function. Once again, we'll put it all in, hit enter, and we get a position of 3.432. And that is our final answer there for part D. We got 2 points for that. 1 point for setting up the integral with the definite integral, and 1 point for the final answer. And that is the end of question number 3 here, this motion question from the 2002 AP Calculus AB exam. All right, this is question number 3 from the 2002 Form B AP Calculus AB exam. And it's a motion question. It's a little bit different. They don't usually have you graph functions anymore, particularly on the calculator portion of the test. They wouldn't have you do this. So this is kind of like a free point. It asks you to graph v of t equals e to the 2 sine t minus 1, knowing that at t equals 0, the particle's at the origin. Well, I mean, this is a calculator question, so, I mean, just go in here and see what it looks like. You don't really need to know what it looks like. Just have your calculator do it for you. So it's kind of a shocking question. I would be utterly shocked if they had you do this. I'm going to set my window to 0 and 16 because that's about what they've got in the graph that they gave you, and my y's from -8 to 8, and just look at the graph. And, well, that's about what it looks like. So we want to cross through. It looks like that's going to be at around, well, it looks like around a little less than, or a little more than 3, a little less than 4. And so we're just going to sketch something that looks like that. So it's gonna go up, have a max. Looks like those maxes were close to 8, but not quite all the way to 8. So something like this, and then it's going to go back up is kind of what this looked like. and then it's going to go back up and come back down. And I mean, they're not going to ask you to do this anymore, but they gave you 1 point back in 2002 for sketching that graph. So don't expect something that nice. In part B, it wants to know during what time intervals is the particle moving to the left? Well, again, this being a calculator question, we can just see when v of t is less than 0. And v of t is less than 0. We'll just look here. Right? It's less than 0 on the intervals from, these points right here, where we hit the x-axis, or the t-axis in our case. And so if we could go through and spend a bunch of time on our calculator trying to solve that, but I think we're going to be better off actually just doing it by hand, figuring out when v of t is equal to 0, because it's kind of a lot of effort to punch it all into your calculator. So e to the 2 sine t minus 1 equals 0, when e to the 2 sine t equals 1. If you take the natural log of both sides, you just get sine t equals 0, or really you just get when the sine of t is 0. Well, sine is equal to 0, we know at t equals 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and then 6 pi is going to be beyond 16, but 5 pi is not. And so those are our places. So we know what all of our intercepts are now if we look back at the graph. Right? So we've got pi to 2 pi, right? From the first one here at pi to the next one at 2 pi, and then from 3 pi to 4 pi, and then from 5 pi to the end of the interval at 16. So we can just say v of t is less than 0 on pi to 2 pi, and 3 pi to 4 pi, and 5 pi to 16. And that's going to be a lot quicker than punching it all in on your calculator this time. And that was worth 3 points. 2 points for just having the intervals, and 1 for the reason that the velocity was negative on those intervals. In part C, it wants us to find the total distance traveled by the particle on the interval 0 to 4. Well, total distance traveled is an integral of speed, which is absolute value of velocity. So we just want to integrate the absolute value of the velocity from 0 to 4. And conveniently, we've already got the velocity function graphed. So when we go out of here, we can just do math. Option number 9, FNINT. We're going to integrate from 0 to 4. And it's going to be the absolute value, which is in the math window and in the second column, option number 1. And we just want that function we've already typed in for y1. So we can hit VARS, the button to the left of clear, go to the second column, and pick function and y1, and then we don't have to retype it. We can just put our dx and get 10.542. And they gave you 3 points for that. And so 3 points for that, and I mean probably 1. They didn't really specify in the scoring guidelines. Probably 2 for the setup and 1 for the final answer there. And in part D, it asks, is there any time on 0 to 16 in which the particle returns to the origin? And you've got to come up with a reason here why it does or does not. And so if we look at this, we know that this is a cyclical function here, right? This is a sinusoidal function. And I mean, it's pretty obvious that if we start at the origin, all this area here at the beginning is a lot more than the little bit that's below here. So we're going to go pretty far to the right, and then just a little bit back to the left, and then a lot further to the right and a little bit to the left. But if we can show that the integral from 0 to pi is a lot more than the integral from pi to 2 pi, at least the absolute values of them, that would prove it. So we know that v of t, we can say, I guess probably the best word for it is v of t is periodic. Right, so we'll call it a periodic function that repeats every, if we look, it repeats every 2 pi. Okay? So it's periodic function, and we'll say period of 2 pi. And we can see what the integral from 0 to pi of v of t is. And we can see what the integral from pi to 2 pi of v of t is. And so we'll have our calculator approximate each of those. So first off, we're going to do math and option number 9. And again, you can just hit 9. You don't have to scroll down. And we're going to do an integral from 0 to pi of y1, which is VARS, the variable button next to clear, the second column, and option 1, and option 1 again. And that one comes out to be 10.107 when you round. And when we do the upper one, from pi to 2 pi, we can go back up here and we can highlight this and bring it back down so we don't have to retype everything. We can put a pi in the lower limit and a 2 pi in the upper limit. And we can see that one is negative 2.067. And so it goes much further to the right first, then left after on each period. So it's never going to return to the origin, so we'll just say so. No. And they gave you 2 points, one for saying no and one for some justification to that. And that is the end here of question number 3, a motion question from the 2002 Form B AP Calculus AB exam. All right, this is question number 6 from the 2002 Form B AP Calculus AB test. This is a motion question of sorts. That's what I'm classifying it as. It's kind of an old question, and there haven't been any super similar to it recently, but that doesn't mean that they won't bring it back anytime soon. So we've got a ship A traveling west towards a lighthouse rock, at a speed of 15 kilometers an hour, and ship B traveling north away from it at 10 kilometers an hour. X is the distance between A and the rock. Y is the distance between B and the rock. And then, of course, we're asked to find the distance in kilometers between ship A and ship B when X is 4 and Y is 3. Well, that's hardly even a calculus problem, right? That's just Pythagorean theorem, right? This is just the square root of 3 squared plus 4 squared, which we should know is 5 kilometers. And of course, no surprise, there's only 1 point for that, because that's way too easy to be on an AP Calculus AB exam. That's a free point right there. In part B, it wants us to find the rate of change in kilometers per hour of the distance between the two ships when X is 4 and Y is 3. Well, we're going to use that same idea of, we'll call this, let's just call it Z here. So we're looking for dz dt, and we know that x squared plus y squared is equal to z squared. Or in other words, if we take the derivative, 2x dx dt, the derivative with respect to t, plus 2y dy dt should equal 2z dz dt. And we're looking for dz dt. So we can, of course, cancel out all the 2's first, just divide both sides by 2. And then all we have to do is put in x, y, z, and dx dt and dy dt to find dz dt. So we can plug in x. X is 4, they gave us that. And dx dt is the rate of change of ship A. Well, it's moving at 15 kilometers per hour towards the lighthouse. Right, so if it's moving towards the lighthouse, that means that the value there needs to be negative, because as that's happening, the value of x is changing by a negative amount. It's decreasing. So we need to put in negative 15 for dx dt. And then we'll add to that our y value, which is 3, times our dy dt. That's 10, and that one is positive because ship B is going away from the rock, so it's an increasing distance. And then we have z, which we just found in part A is 5 times dz dt. So we end up with negative 60 plus 30 on this side, negative 30 equals 5 dz dt, or dz dt is negative 6 kilometers per hour. And they gave you 4 points for that. 1 just for having this distance expression, 1 for differentiating with respect to t, right? So, or sorry, not 1, but 2 for that. And then 1 for getting the final answer there. And in part C, it says, let theta be the angle shown in the figure, and we want to find the rate of change of theta in radians per hour when x is 4 and y is 3. So there's lots of ways to go about doing this. So we can use basically any trig function that we want here. Doesn't really matter. I think I'm going to choose using, we'll just use sine of theta. So if I let the sine of theta equal the opposite, which is y. Oh, actually, let's just, yeah, I guess sine theta is fine. We'll use y over z for sine theta. Then to take the derivative here of sine of theta with respect to t, we're going to get cosine theta d theta dt. And then the derivative of y over z is just going to be a quotient rule problem, right? So the quotient rule says take the denominator and multiply it by the derivative of the numerator. So that'll be z dy dt minus, so we did denominator times derivative of numerator minus numerator times derivative of denominator all over the denominator squared. And so now we can just plug everything in to find d theta dt. We know what cosine theta is because cosine, right? Cosine theta is equal to x over z. Well, for our purposes, x was 4, right? And when we did this before, right, we got z was equal to 5, not here, but back here, right? So, and dz dt was equal to negative 6. So we're going to have z as 5. So we're going to have our x 4/5 of d theta dt is equal to z, which is 5, times dy dt, and we already knew dy dt was 10, minus y, which we know is 3, times dz dt, which we got negative 6 for, all divided by z, which was 5 squared, so 25. Now we're going to just simplify all this down. And so I think it'll be easier for us if we put this on a new page because we're kind of running out of room here. So we had 4/5 d theta dt. We'll keep that here for now. Is equal to, and then it was 5 times 10 or 50 minus 3 times negative 6, so plus 18. All over 25, or d theta dt is going to equal, well, that's 68 over 25 times 5 over 4. And so we should be able to just simplify that down. The 5s will cancel out a little bit there. So right, this is, if we divide the 5 into 5, we're going to end up with a 68 in the numerator and a 4 times a 5 down here. And then 68 over 4, we should be able to divide 68 by 4 17 times. So this is 17/5, and this is in radians per hour. Right? Never in degrees, in radians here. And that was worth 4 points there. So they gave you 1 for having an expression for theta in terms of some variables here. And we used y and z. And then a differentiation with respect to t, again, was worth 2 points. And then your final answer was worth 1 point. And that's the end of this motion FRQ, which was 2002 Form B AP Calculus A exam, AB exam problem number 6. All right, this is question number 2 from the 2003 AP Calculus AB exam. This is a motion question. It's a calculator question. And in part A, they just want us to find the acceleration of a particle at t equals 2, at least to start with, given this velocity function. So we know that the acceleration of a function is just the derivative of the velocity. So we can use our calculator to just take the derivative of this at 2. So we'll use our graphing calculator, and we'll say math, and we'll go down to option number 8 in deriv, and we'll take the derivative with respect to x of our velocity function, which was negative t plus 1, and we'll use x plus 1 here. And then it's the sine of x squared over 2. And I apparently didn't hit the right thing there. The sine of x, let's try that again. There we go, x squared over 2. There we go. So we'll close our parenthesis. Apparently we somehow have 2 parentheses on our sine. Not sure how that happened, but that shouldn't be an issue. And we want this at x equals 2. And we end up with 1.588 when we round. And then it says, is the speed of the particle increasing at t equals 2? Well, speed increases when the velocity and acceleration have the same sign. So we'll note that the acceleration is positive. And then we'll find v of 2. Well, v of 2, rather than type it all in at once, I'm just going to say, if we plug in 2 here, it's negative 3 sine of 2. And if you're not sure if that's positive or negative, well, just go ahead and put it into your calculator and see. Negative 3 sine of 2 is negative 2.72789. You don't need the exact value of it. You can just say it's less than 0. And you can say, so speed is decreasing at t equals 2 because v of 2 and a of 2 have opposite signs. And you got 2 points there, 1 for the value of a of 2 and 1 for the answer with the reason. In part B, it wants you to find all time t in the open interval when the particle changes directions. So what we first need to do is see when v of t is equal to 0, so that we can see when velocity might have a sign change. And of course, we can do this on our calculator, or we can just do this by hand. Since it's a calculator question, I'm going to just go into y equals and graph it. So we're going to graph our function, which was negative x plus 1, and it's the sine of x squared over 2. And so that's what we want to graph. And we're talking about the interval from 0 to 3. And so we're going to hit window and do an x minimum of 0 and an x maximum of 3. And when we graph it, we can see it looks like it changed signs only one time over there, maybe around 2.5. So we'll hit second, trace, and calculate the 0, option number 2. We'll scroll to the right till we're pretty close to that intercept. And we'll hit enter. And then we'll scroll further to the right, past the intercept. Oh, not that far past the intercept. Good enough. Oh my gosh, I don't know what it's doing. Let's slow this down here. There we go. All right, and hit enter. Hit enter a third time, and you get 2.507. And we know that it's changing directions there because we can see that the velocity was negative before that, and then the velocity was positive after that. And so we can say it changes directions at t equals 2.507 because, and we could say v of t goes from negative to positive. And you got 2 points for that, 1 for the value and 1 for the reasoning. In part C, it wants the total distance traveled by the particle from 0 to 3. Well, total distance traveled is always an integral of the speed, and speed is the absolute value of the velocity. So we're just going to integrate the absolute value of the velocity from 0 to 3. And here's the reason why I decided to just graph it and not solve that first part, or part B, by hand, because now in my y equals, I've got the function. So now I don't need to retype it every time I need to use it. So what we want to do is just math option number 9 for an integral. We're going to go from 0 to 3, and we want the absolute value of the velocity. So we can find absolute value in the math window right there under alpha. And in the second column, it's just the first option. And then now, instead of retyping the velocity function, we can hit the VARS button, stands for variables, just to the left of clear. And if we go to the second column for y variables and hit enter, we can see that our function y1 can just be inputted without having to retype it. We'll put our x outside, and we'll integrate, getting 4.334. And that is our total distance traveled, and that was worth 3 points. 1 for the right limits, 1 for the right integrand, and 1 for the answer. In part D, we want to know what is the greatest distance between the particle and the origin. Well, the only time we could be at our greatest distance is places where we change directions, right? And so that's going to be at that value we found earlier, where we changed directions at 2.507 in part B, right? And so that's when we're going to be furthest away from the origin, so we can find the greatest distance by just finding the displacement of the particle from 0 to 2.507, and we find displacement by integrating the velocity. So we'll just integrate velocity on that interval. So we're going to hit math, option 9. We're going to go 0 to 2.507. And we're just going to do the velocity function. So we'll hit VARS again, go into the second column, option 1, and then option 1 again. And we'll integrate that. We can see that it displaced 3.265482193. We'll just call it 3.265. Right? But we'll note that at the beginning, I believe that was a negative. Yeah, it was a negative 3.265. We started at a position of 1. So really our position here is at negative 2.65. So the position is negative 2.265 because we need to subtract that 1. We displaced 3 units to the left, but started at 1. And so we're going to be at negative 2.265. And we could test to see the position at 3. But if we look at the graph here, it's pretty clear that there's more area under the curve from 0 to 2.5 than there is from 2.5 to 3. And the particle's still going to be to the left there at 3. And we could even be certain of that, right? Because we know what the total distance that it traveled was. Right? The total distance that it traveled was 4.334, right? If we look at part C. And so if we already had gone 3.265, and then we're at a position of negative 2.265, we don't have that much more left to go 4.33, only 1 more unit back to the right. And so we're still going to be to the left of the origin. And thus, we are not going to be going further beyond the origin to the right where we may not where we may be further away from than 2.265. And so that is worth 2 points. 1 for the total distance it travels and 1 for the actual answer. And that is the end of this motion question, which was question number 2 from the 2003 AP Calculus AB exam. All right, this is question number 4 from the 2003 Form B AP Calculus AB exam. It's a motion question, and we're given a particle moving along the x-axis with its velocity for t greater than or equal to 0 given by this v of t function, which is -1 plus e to the 1 minus t. We want to find the acceleration of the particle at t equals 3 first. So acceleration, we know, is always equal to the derivative of the velocity. I don't know why I wrote a dt there. That's a good question. Too many integrals today. So a of t equals v prime of t. So we'll just take our derivative. And the derivative of -1 is 0. And the derivative of e to a function is e to the function times the derivative of the function. So the derivative of 1 minus t is -1. So to find a of 3, it's just negative e to the 1 minus 3, or negative e to the -2. And you got 2 points there. 1 point for taking the derivative correctly and 1 point for evaluating correctly. In part B, it asks, is the speed of the particle increasing at t equals 3? Well, we already just found that a of 3 was a negative value. And then we need to check what v of 3 is. So v of 3 is equal to -1 plus e to the -2, or -1 plus 1 over e squared. Well, 1 over e squared is less than 1. So if we do -1 plus something less than 1, we still get a negative value. So both the velocity and the acceleration are negative. So that means that the speed is increasing, right? The speed is increasing when the velocity and acceleration have the same sign. So we'll say the speed is increasing because we'll say v of 3 and a of 3. You can either say are both negative or have the same sign. Either one is acceptable, doesn't really matter. And I'll just put in parentheses here, both negative would also work. And they gave you 1 point there for the answer with the reasoning. In part C, we want to find all values of t at which the particle changes directions. So the first thing we have to do is just set the velocity equal to 0, because our direction can't change unless our velocity equals 0. So that'll be -1 plus e to the 1 minus t equals 0. But we'll add 1 to both sides to get e to the 1 minus t equals 1, and take the natural log of both sides, right, to get 1 minus t is 0, or t equals 1. And so we have to determine if there is actually a sign change of the velocity at 1. So we can make a sign chart with 0, 1, and we don't need to put anything on the other end. If we put in something more than 1, like, let's say 1,000,000, we have -1 plus e to the 1 minus 1,000,000. So negative, well, really big number, right? More 9s than that, of course, but I'll throw one more in there. And -1 plus 1 over e to that power is clearly going to still be a negative value. So our particle is moving to the left. And if I put in something like 1/2, now we have -1 plus e to the 1 minus 1/2, or e to the 1/2. Well, -1 plus the square root of e. The square root of e is more than 1, so when I add that, we get a positive. So we do change directions at t equals 1. So we can say it changes directions at t equals 1. Because v of t goes from positive to negative. Or you could say, v of t is greater than 0 on 0 to 1. V of t is less than 0 on 1 to infinity. And that was worth 2 points. 1 just for getting t equals 1 as a possibility, and 1 for your justification of it. And in part D, it asks us for the total distance traveled by the particle on this interval. Well, total distance traveled is an integral of the absolute value of the velocity. Well, we knew that the velocity already, just from looking at the previous problem, the velocity was positive on 0 to 1, but negative on 1 to 3. So since we don't have a calculator for this problem, we have to break this up into an integral from 0 to 1 of v of t dt, and then we're going to subtract the integral from 1 to 3 of v of t dt, because that's when it is negative. So making it the opposite of that integral turns those negative values into positive values. And so we'll just integrate here v of t, right? And so if we do that, integrating v of t, negative 1's integral is just negative t. And the integral of e to the 1 minus t, well, when we integrate e to the 1 minus t, that's like e to the u, where u is 1 minus t. So du is negative 1 dt. So we need to put a negative on here. And, that's going to, if we integrate that now, it's negative integral e to the u du, which is just negative e to the u, or minus e to the 1 minus t. So that's our integral here of negative 1 plus e to the 1 minus t. And we're going to evaluate that from 0 to 1. And then we're going to subtract that, evaluated from 1 to 3. So if we plug in 1, we get negative 1 minus e to the 0. And then minus 0 minus e to the 1. And then minus this whole thing, which is going to be negative 3 minus e to the negative 2 minus negative 1 minus e to the 0 when we plug it all in. And so, first of all, we got negative 1 minus e to the 0. So that's negative 1 minus 1. That's negative 2. Minus a minus e is going to be plus e. So we've got negative 2 plus e. And on this side, we have a minus 3. And we also, so we'll just put that, we have plus 3. And we have minus a minus e to the negative 2. So that'll be a plus e to the negative 2. And then we have a minus 1, which is going to be a minus 1. And we have a minus e to the 0, which is going to be another minus 1. So it looks like what we end up with is negative 2 plus 3 is 1 minus 1 is negative 1 plus an e to the negative 2. And we got a total of 4 points for part D here. You got 1 point for having the right limits here. And we got 1 point for having the right integrand. We got 1 point for the correct anti-differentiation and 1 point for the final answer. And that is the end of this motion FRQ, question number 4 from the 2003 Form B AP Calculus AB exam. All right, this is question number 3 from the 2004 AP Calculus AB exam. This is a motion question. And we've got a particle moving along the y-axis with velocity for t greater than or equal to 0 given by v of t, which is 1 minus the inverse tangent of e to the t. And we're given an initial position that when t is 0, the position of the particle is -1. Part A just wants us to find the acceleration of the particle at t equals 2. Well, we know that acceleration is just the derivative of the velocity. So if we want the derivative of the velocity at 2, we can just take the derivative there and evaluate it at 2. Conveniently, this is a calculator question, so we don't even have to worry about finding the derivative by hand. We're going to go to our calculator. We're going to hit Math. We're going to go down to option number 8 in deriv. We'll do a derivative with respect to x, even though our function's in terms of t. That's how we do it on the calculator. We always do them in terms of x. Our function was 1 minus the inverse tangent of e to the t. So we'll do e to the x. And we wanted to find this at x equals 2. So we'll just hit enter there and get negative 0.133. And they just gave you 1 point here for the answer in part A. In part B, it asks us if the speed of the particle is increasing or decreasing at t equals 2. Well, we already knew that a of 2 is less than 0. And so to determine if the speed is increasing or decreasing, we also need the velocity at 2. So we'll see what v of 2 is. V of 2 should be 1 minus the inverse tangent of e squared. So we'll punch that into our calculator. Right? 1 minus the inverse tangent of e to the second power. And we get negative 0.436. Which is also negative. And speed increases when velocity and acceleration have the same sign. So we'll say, so speed is increasing because a of 2 and v of 2 have the same sign. And they just gave you 1 point here for the answer with your explanation in part B as well. In part C, we want to find the time at which the particle reaches its highest point. Well, in order to figure out when a particle's position is at its maximum, right, that's when its velocity is going to equal 0. That'll be when it'll have a maximum or a minimum on the position of something, and when its derivative, the velocity, equals 0. So we want to see, when does v of t equal 0? And so we can just go ahead and use our graphing calculator to find that value. We can also find an exact value by hand if we want to. It wouldn't be that tough to do, but we might as well just graph it here. So we've got y equals, what was our function? It was 1 minus the inverse tangent of e to the t, or in our case, e to the x. And we weren't really given an interval here, so we'll just graph it on the standard calculator graphing here. Although maybe it's better, like, we were looking at, all of our stuff was like between 0 and 2, but we can see that like this is going to be less than 0 most of the time. But maybe if we zoom in, hit zoom in option 2 around the origin, we can see that it does have an x-intercept there. We do have one critical value. So we're going to hit second trace. We're going to go to option 2, which is 0. And we'll go a little bit to the left, or to the right. Make sure we're to the left still, though, of the intercept, and hit enter. Then go a little to the right of the intercept and hit enter. And hit enter a third time, and we get 0.443027. So that's when our velocity is equal to 0. And we saw in the sign chart that v of t was greater than 0 on 0 to 0.443027. And then v of t was less than 0 on 0.44302227 to infinity. So the position is at a max, not on, but at t equals 0.44302227. If the velocity is positive, it's going up, and then the velocity is negative, it's going down, right? And so that max must be at 0.44302227. And we got 3 points for this. 1 for just setting v of t equal to 0, 1 for identifying the candidate, and 1 for justifying that it was a max, right, by talking about the sign of the velocity there. And in part D, we want to find the position of the particle at t equals 2. And then we want to know, is the particle moving toward or away from the origin at that time? So to find the position of the particle at t equals 2, well, displacement is an integral of velocity. So if I integrate the velocity from 0 to 2, and I'm picking 0 because I know what the position at 0 is already, that should give me the position, and we'll call it y of 2 minus y of 0. Or in other words, if I want to find y of 2, the position at time t equals 2, I just need to add y of 0 over to the left and get y of 0 plus the integral from 0 to 2 of v of t dt is equal to y of 2. And then, of course, we'll just use our calculator to find what that value is. So y of 0 was -1. So we'll say -1 plus the integral, so math and option number 9, the integral from 0 to 2 of our function, which was once again 1 minus the inverse tangent of e to the x dx. And that gives us a position of -1.361. And we already knew that the velocity at 2, if we go back to part B, our velocity at 2 was negative. And so if our position is negative and our velocity is negative, we must be moving away from the origin. So we can say it is moving away. And you can say because y of 2 is less than 0 and v of t is less than 0. Or you could say something like it is below the origin and moving down, right, is what that means. And that was worth 4 points. 1 for just using the integral from 0 to 2 of v of t, 1 for having the initial condition in there somewhere, 1 for the value, and 1 for moving away with a reason. And that is the end here of this motion FRQ, question 3 from the 2004 AP Calculus AB exam. All right, this is question number 3 from the 2004 Form B AP Calculus AB exam. It's a motion question. We've got a chart here of values of a plane that's flying in a straight line with a positive velocity given in miles per minute. We know that v is a differentiable function, and we got the values from 0 to 40. We want to use a midpoint Riemann sum with 4 subintervals of equal length to approximate the integral from 0 to 40. So 4 subintervals of equal length will be 0 to 10, 10 to 20, 20 to 30, and 30 to 40. And so we'll use our midpoints here of 9.2, 7, 2.4, and 4.3. Of course, each of those are equal length, so we can just do 10 times all of them added together. Right, so that'll be 10 times 9.2 plus 7 plus 2.4 plus 4.3. And if you add all that together, You got 16.2 from the first two, and then 18.6, and then 22.9 multiplied by 10 gives you 229. And it asks us, with correct units, what's the meaning of this? So if it's asking us what's the meaning of this, well, since this is always positive values here, right? If we have a positive velocity all the time, then it's just going to be the distance that this plane flies. So the meaning is the integral from 0 to 40 of v of t dt is the distance in miles the plane flies during the 40 minutes. And they gave you 3 points actually for this. 1 for the setup, 1 for the value, and 1 for the explanation using the correct units. In part B, it says, based on the values in the table, what is the smallest number of instances at which the acceleration could be 0? And so we know that the acceleration is going to be 0. That's the derivative of our velocity, right? It can be 0 whenever our velocity function goes from increasing to decreasing, right? And so because then its derivative would have to be equal to 0 since this is a differentiable function. And so, we would basically say something like v prime of t, which is a of t, can equal 0 if v, we would say something like if v goes from increasing to decreasing, or vice versa. And so we can see that happens. Let's see, we're increasing from 0 to 5, 7 to 9.2. And then from 5 to 10, we're still increasing. But from 10 to 15, we go back down. So we can say this happens on the interval 5 to 15, because we went up here, but then down here. And then we continued, so we go up, and then we went back down, and we're still going down, and we're still going down, and then we were flat here, and then we went back up, right? And so it must have also happened somewhere between 20 and 35, because we went down and then back up. So we'll say and 20 to 35, so at least 2 times. And they're going to give you 2 points for this, 1 for saying 2 times and 1 for an explanation. In part C, we've got a new function here, f of t, 6 plus cosine t over 10 plus 3 sine of 7t over 40. That's now a new model for the velocity. And we want to know what's the acceleration, if that's the velocity, at t equals 23. So all we really want is just f prime of 23. And you could go and do all this by hand, but since this is a calculator question, we're just going to take the derivative of that at 23 on our calculator. So we're going to do math, and we're going to do option number 8. And we're going to take our derivative with respect to x here of our function 6 plus, and it is cosine of x over 10, and then it was plus 3 times the sine of 7x over 40. And we're going to evaluate this. It wanted us to find this at x equals 23. And so we get negative 0.408 when we round. And of course, this is in miles per minute or miles per minute squared, right? Because we've taken the derivative of something that was in miles per minute with respect to time. And you just get 1 point there for that answer with the correct units. Now here in part D, we want to know the average velocity using that same model from part C, that same function. Well, the average of a function is just 1 over b minus a times the integral from a to b of that function. So we're just going to do that. 1 over 40 minus 0 times the integral from 0 to 40 of f of t. We'll punch it into our calculator. So we're going to do math. We're going to go down to option number 9, FNINT. We're going to do 0 to 40. And then we'll put in our function, which again was 6 plus the cosine of x over 10 plus 3 times the sine of 7x over 40 dx. And then, of course, we wanted to do 1 over 40 times this, so we'll just divide by 40 here at the end, and we get 5.916. And, of course, if we want to put the units, they've given them to us anyway. It's miles per minute. And they actually gave you 3 points for this, 1 for having the correct limits of 0 to 40, which seems pretty straightforward, 1 for having f of t inside the integral, and 1 for the final answer. And that is the end of question number 3 here, this motion FRQ from the 2004 Form B AP Calculus AB exam. All right, this is question number 5 from the 2005 AP Calculus AB exam. This is a motion question. We've got a car traveling on a straight road from t equals 0 to t equals 24. And we've got its velocity in meters per second. And we don't have an explicit function for it, but we've got a graph of this piecewise linear function, which kind of looks like a nice little trapezoid there. And we want to find the integral from 0 to 24, and then with correct units explain what it means. Well, the integral from 0 to 24 is just the area underneath that curve. And so it does look just like a trapezoid. So we can find that area underneath the curve just by finding the area of that trapezoid. So it looks like the base on the bottom, and they probably in the scoring guidelines like cut it up into 2 triangles and a rectangle, but I don't see any reason why you'd want to do that. They often do that for these. I mean, it's just a trapezoid with a base of 24 and a base going across the top from 4 to 16. Right, so 0 to 24 is our 24, 4 to 16 is 12. Divide that by 2 and multiply by the height of 20. Right? Well, that's just 24 plus 12, which is 36, times 10. So we just get 360. Our units here are going to be meters. And what does this mean? Well, the integral of velocity is normally a displacement. But since it's always positive, it's just how far the car went. So we can just say the integral from 0 to 24 of v of t dt tells us that, says the car travels, we'll say 360 meters in those 24 seconds. And make sure you have units on both things there, because it does say with the correct units. You got 1 point for the answer and 1 point for the explanation with the units. In part B here, it says for v prime of 4 and v prime of 20, find the value or explain why it doesn't exist. And so v prime of 20 is a quick, easy one. V prime of 20 is just the slope of the function, the velocity function at 20. So that's just the slope between the point at 1620 and the slope, or the point at 24, 0. So we'll just do our our value at the second point, so that's 0. Our y value there is 0 minus our y value of 20 over 24 minus 16. Well, that's negative 20 over 8, which of course that reduces, we can divide them both by 4, into negative 5 halves. And our units here, there was meters per second initially for velocity, so when we do acceleration, when we take a derivative with respect to time, we have another second that we're, per second, so it's meters per second squared. And then for v prime of 4, if we just look at the graph, we can see that there's a corner there at 4, which tells us that the derivative doesn't exist, right? But that's not a good enough explanation, just that there's a corner there. And what we have to do is we have to look at the limit of the slopes on both sides, right? So like we can say that the limit as t approaches 4 from the left of that slope, right? So we just find that slope of v of, we'll say v of t minus v of 4 over t minus 4. Well, that slope there is always, from whatever t value we're looking at as we get close to 4, that slope is always just the slope of the line from 0, 0 to 420. That's a slope of 5. And that does not equal the other slope on the other side, right? The slope on the other side, as we approach from the right-hand side of the same thing, that equals 0. Like we can see that's a horizontal line. That slope is 0. So just note that the slopes are not the same approaching both sides, and you should get all 3 points here. 1 for saying it doesn't exist with an explanation, 1 for getting negative 5 halves, and 1 for the correct units. In part C, we've got a of t as the acceleration, and we want to write a piecewise defined function for a of t. Well, that should be pretty straightforward. It's just the slopes here. So a of t, we've already found most of them. In fact, we've actually already found all of them. A of t, on the first part from 0 to 4 is just always equal to 5. We just found that slope a minute ago. So we'll say it's 5 if we have 0 to 4. And then it's 0 if we are on that horizontal piece, which is 4 to 16. And then we also found it to be negative 5 halves on the last piece. So that'll be 16 to 24. And that's it. I mean, you get 2 points for doing all of that, right? We've got the 3 correct constants. We've got the right intervals. And we didn't include the values at 4 and 16, right? We have open intervals at 4 and 16, and at 0 and 24 because they told us open interval. But at 4 and 16, we know that the acceleration doesn't exist there because we had corners. And so we don't have to note that, but just make sure you didn't put an or equal to at 4 or 16. In part D, it asks us to find the average rate of change of v over the interval from 8 to 20. And so we want to know, does the mean value theorem guarantee a time when the derivative of the velocity is equal to that average rate of change? And so our average rate of change should just be v of 20 minus v of 8 over 20 minus 8. Well, 20 minus 8 is 12. V of 20, well, v of 20 right here, if we were going down by 5 every time we went over 2, right, the slope there was negative 5 halves, then we've gone over 4 units, so we need to go down 10 units from our 20, right? So that's going to be 10 for v of 20, and v of 8, we know v of 8 was 20. So what we've got here is 10 minus 20 is negative 10 over 12, or negative 5/6. It doesn't say to indicate units there, but it would be meters per second squared if we wanted to. And the question then says, does the mean value theorem guarantee a value such that v prime of c is equal to this average rate of change? And v is continuous, but we know that v is not differentiable at 16 because of the corner. So we can say no, the mean value theorem does not apply on this interval we'll say on 8 to 20. And the reason is because v of t is not differentiable at t equals 16. Right? And 16 is on our interval, and therefore we can't apply the mean value theorem. And so 1 point for the average rate of change and 1 point for your answer of no with an explanation. And that is the end here of this motion FRQ, which was question number 5 from the 2005 AP Calculus AB exam. All right, this is question number 3 from the 2005 Form B AP Calculus AB exam. This is a motion question. We've got a particle moving along the x-axis, and we've got its velocity, v of t, for t equals 0 to 5. Right? The velocity is the natural log of t squared minus 3t plus 3. We're also given an initial position that at x equals 8, that at t equals 0, the particle is at x equals 8. Part A just wants us to find the acceleration of the particle at t equals 4. Well, the acceleration is just the derivative of the velocity. I don't know why I put a 1 down there, v prime of 4. And since this was a calculator question, you can just use your calculator to find this derivative. Now that's a derivative you should be able to do really easily by hand. But if it's a calculator question, I suggest you just use your calculator to do it, because there's no reason not to, right? I mean, you might make an error with your derivative otherwise. So just type it in here, in deriv, math option 8, the derivative with respect to x of the natural log of t squared. So we'll do x squared minus 3t. So we'll do minus 3x plus 3, and we wanted it at x equals 4, and we get 0.714285715. Now, knowing what that is, we could, you can always turn that into a fraction by hitting math and option number 1, right? And so we'll see that it didn't do it for us, but that fraction is actually real close to 5/7. That is 5/7. So we could say 0.714, or you could have just done the derivative. Right, and just to note that v prime of t, which is a of t, right, we could just do 1 over t squared minus 3t plus 3 times the derivative of that, which is 2t minus 3. And if you plug in 4 to that, you can see you end up getting, if we evaluate this at t equals 4, we get 5 in the numerator. In the denominator, we have 16 minus 12 is 4 plus 3 is 7. So they'll accept either answer here because it's a calculator question. It's just worth 1 point. You don't need to do it both ways. One way or the other is fine. For part B, we want to find all times t on the open interval 0 to 5 when the particle changes direction, and then we want to know when is it traveling to the left. Well, all we have to do here is just set the velocity function equal to 0. Now we can do this on our calculator, or we can do this, we can also just do this by hand if we wanted to. So if we think about it, the natural log of 1 is equal to 0, right? So what we need is the thing inside the natural log to equal 1. So if we set t squared minus 3t plus 3 equal to 1 and solve that, right, we just get t squared minus 3t plus 2 equals 0. Factor to t minus 2 and t minus 1. We get the places where it changes directions potentially are t equals 1 and t equals 2. And so what we need to do is we actually need to like make a little sign chart here. Now, if you did this on your calculator, you'd be able to just look at the graph of the velocity and see when it's positive and negative there. But we'll test it here. If I take something between 0 and 1, like a half, if I take a half in here, I'm going to get, I'm going to get 1/2 minus 2 is a negative 3/2. And then 1/2 minus 1 is a negative 1/2. So I have negative 3/2 times negative 1/2, which is positive 3/4. So I'm going to be taking the natural log of 3/4. Well, that's the natural log of something that's less than 1. So that's going to come out to be negative. And then is that right? I think I did that somehow incorrectly there. Yeah, what do we put in? We put in 1/2. Negative 3/2 times negative 1/2 should be positive 3/4. Because I actually did not put that into the right thing. If we should be careful here. If we're putting in 1, we got to put it into the actual velocity function. I was putting it into my equation that I solved. So if I put in like a half into that, we end up with the natural log of 1/4 minus 3/2 plus 3. Well, 1/4 minus 3/2 is going to be 1/4 minus 6/4. That's going to be negative 5/4. And we add 3 to that, we're going to certainly get a number that is more than 1. So this is greater than 0. So we're going to be positive on 0 to 1. So be careful on that. Make sure you actually use the right function. If you put in something like 3/2, right, you're going to get the natural log of 3/2 squared. So the natural log of 9/4 minus 3 times 3/2. So that'll be minus 9/2 plus 3. So that's 9/4 minus 18/4 is negative 9/4 plus 3. Negative 9/4 plus 3 is going to be 3/4, and 3/4 is less than 1. So when I take the natural log of it, I get a negative. And if we put in something more than 2, like 3, we get the natural log of 9 minus 9 plus 3. Natural log of 3 is positive. So the places where it changes directions, and we'll write this out, we'll say the particle changes directions at t equals 1 and t equals 2 because v of t changes signs. And then we'll also say it also wants to know when is it moving left. It moves left when its velocity is less than 0 on, that's the interval from 1 to 2. And so that kind of answers everything it asks. We get 1 point for just setting v of t equal to 0. And any form of this here, right, like noting that natural log of 1 is 0 and setting t squared minus 3t plus 3 to 1 is the same thing. So you get 1 point for that, 1 point for the direction change values, and 1 point for the interval 1 to 2 with a reason. All right, now here in part C, it wants us to find the position of the particle at t equals 2. And so to find a position, we just have to integrate the velocity, right? The integral of the velocity is the displacement. So if we integrate the velocity from 0 to 2, and I'm picking 0 because I know the position at 0, and I'm picking 2 because we're looking for the position at 2, that should be the position, which we'll call it x, at 2 minus the position at 0. Well, we're looking for x of 2, so x of 2 should just be x of 0 plus that integral from 0 to 2 of b of t dt. And x of 0 is, of course, 8. And so we're just going to use our calculator, because this is a calculator question. We're just going to do 8 plus the integral from 0 to 2 of our function. So we've got 8 plus math, option number 9 for the integral. 8 plus the integral from 0 to 2 of our velocity function, which was the natural log of x squared minus 3x plus 3 dx. And that gives us 8.369, which should be our position. And they gave you 3 points there for that. 1 just for having the integral of v of t from 0 to 2. 1 for dealing with the initial condition, and 1 for the final answer. And in part D, it asks us for the average speed of the particle on this interval from 0 to 2. Well, speed we know is the absolute value of velocity. So if we want the average of that function, absolute value of velocity, we just do 1 over b minus a times the integral from a to b of the speed. Right? The average value of a function is just the mean value theorem for integrals. And so since, again, this is a calculator question, we'll just go in and we'll put a 1/2 out in front. That's the same as 0.5, so I'll just put 0.5. Math, option number 9 for an integral from 0 to 2. We want absolute value of this natural log function, so we hit math, and we go over to the second column for absolute value, number 1 there. And then we'll just put in our function, natural log of x squared minus 3x plus 3. We'll close off our parenthesis for the natural log. We'll go outside here and put our dx, and we get 0.371 when we round. And that was worth 2 points, 1 for the correct integral setup and 1 for the final answer. And that is the end here of this motion FRQ, which was question number 3 from the 2005 Form B AP Calculus AB exam. All right, this is question number 4 from the 2006 AP Calculus AB exam. This is a motion question, and we're given a chart of values here. We've got rocket A with a positive velocity that's being launched upward from an initial height of 0 at t equals 0. And we're given some selected values of t on the interval from 0 to 80 seconds. We want to find the average acceleration of the rocket, right? So, well, if we think about that, the average acceleration, right, is 1 over b minus a, so 1 over 80 minus 0, times the integral of the acceleration from 0 to 80. And you don't need to necessarily write this setup, noting that that's going to be 1 over 80 times the integral of acceleration, which is velocity. So velocity at 80 minus velocity at 0. So velocity at 80, according to our chart, is 49. And velocity at 0 is 5. So we have 49 minus 5 divided by 80. That's 44 over 80. Divide those both by 4. You get 11 over 20. It says indicate units of measure. So the velocity was in feet per second. If we take a derivative of that, or if we divide it by a number of seconds, not take a derivative, but divide it by a number of seconds, right, 80 seconds, that should become feet per second, or feet per second squared. And they just gave you 1 point there for the answer of 11/20. And the units, you had to have the correct units in parts A and B to get a point for the units. So we'll note that as we come here to part B. Using correct units, explain the meaning of the integral from 10 to 70 in terms of the rocket's flight. Well, we know that the velocity is always positive. I had already told us that. So an integral of a velocity that's always positive is going to tell us how far this rocket has flown. Normally, an integral of a velocity just tells us a displacement because the velocity could be positive or negative. But since it's a positive velocity, the integral from 10 to 7 of v of t dt just tells us, tells us the distance, and it says using correct units, so we'll say in feet. The rocket travels on t equals 10 to t equals 70 seconds. Make sure your 70 looks like a 70, not like a 20, like mine did. 70 seconds. Because we might make the note because v of t always positive, right? So that's why we know it's a total distance traveled, not just a displacement like an integral of velocity normally is. And so then it says, use a midpoint Riemann sum with 3 intervals of equal length to approximate that. So 10 to 70 with 3 of equal length, that's going to be 10 to 20. 10 to, not 10 to 20. That's going to be 10 to 30, 30 to 50, and 50 to 70. And a midpoint Riemann sum just says take the width of each interval, which is going to be 20. And in fact, I'm going to write, it's always good to do this, the integral from 10 to 70 of v of t dt is approximately equal to, that first width from 10 to 30 is 20, times the midpoint, the velocity at the midpoint of there is 22, right? And then the next one from 30 to 50 is another 20, and the midpoint there, the velocity is 35. And then, of course, from 50 to 70 is also 20, and the midpoint there is 60, so the velocity at 60 is 44. And so if we just do all of those things together there, let's see, 20, they're all getting multiplied by 20, so 44 and 35 is 79. 101, if we add the 22 to it, 101 times 20 is going to be 2020. And it doesn't ask for the units in the second part of it, but we'll say 2020 feet. So we're getting 1 point here for our explanation, 1 point here for using the correct values in the right setup here, and 1 point for the right final value, plus 1 point for the units from A and B here, at 1 point for that. So we've now already got 5 points here just from parts A and B. Now our last part of this question here, part C, says the rocket is launched upward with an acceleration of 3 over root t plus 1 feet per second per second. Now, if you hadn't know what the units were supposed to be in part A for acceleration, right, well, there you go. There's your units for acceleration right here. You could have just found it in part C. And it tells us that at t equals 0, the initial height is 0, and the initial velocity is 2. Right? So this is a different rocket, right? Which of the two rockets is traveling faster at t equals 80? Well, if we want to find the velocity at 80, we just need to integrate the acceleration from 0 to 80. Right? So we're going to integrate 3 over root t plus 1. And that's going to tell us, well, the integral of acceleration is velocity. We'll call it v sub b. And it should be v sub b at the upper limit minus v sub b at the lower limit. And so that tells us that if I'm looking for the velocity of rocket B at 80 seconds, I just need to add v sub b of 0 out to the front. So v sub b of 0 plus the integral from 0 to 80 of 3 over root t plus 1 dt should equal v sub b of 80. Well, v sub b of 0, the initial velocity was 2 feet per second. And then if we integrate 3 over root t plus 1, I'm going to just do this off to the side.
the integral of 3 over root t plus 1, that's a u substitution where u is t plus 1 and du is just dt. So really this is just an integral of 3 u to the negative 1/2 du. And if you integrate 3u to the negative 1/2, we're going to get 6u to the 1/2, or 6 root u. So this is 6 root u, or 6 root t plus 1, evaluated from 0 to 80. So we've got 2 plus 6 root 81 minus 6 root 1, which gives us 2 plus, well, square root of 81 is 9. 6 times 9 is 54. So we got 6 plus 54 minus 6, which looks like that comes out to be 50. And we'll note that that tells us that v sub b of 80, which is 50, is greater than v of 80, which was 49. Right? And so we could say rocket B is traveling faster. I've kind of run out of room here, so I'm just going to write it up here. Rocket B is traveling faster. And they gave you 4 points for this question here. 1 point is for getting the correct integral here, 6 root t plus 1. 1 point for, it says the constant of integration, but if we did a definite integral, you're perfectly fine to use the definite integral here. So 1 point for then having the actual v sub b of 0 here, and then 1 point for turning it into a 2, and then 1 point for finding it to be 50 and having the correct conclusion. And that's the end of question number 4, this motion FRQ from the 2006 AP Calculus AB exam. All right, this is question number 6 from the 2006 Form B AP Calculus AB exam. It's a motion FRQ here. And we're given a chart of t values from 0 to 60, and we're also given the velocity and the acceleration at those selected points of a car traveling on a straight track. We're talking about feet per second and feet per second squared as our units for velocity and acceleration, respectively. So it asks us first to, using appropriate units, explain the meaning of the integral from 30 to 60 of the absolute value of v of t dt. And so the integral of absolute value of velocity is an integral of speed. And an integral of speed always tells us a total distance traveled. So we're going to say the integral from 30 to 60 of the absolute value of v of t dt is the total distance traveled by the car on the interval, and total distance traveled by the car, and we should say in, our units were feet, so in feet, on the interval from 30 to 60 seconds. So it says using appropriate units, so we want to make sure that we say the total distance in feet, and we want to make sure we say 30 to 60 seconds. So we get 1 point for that explanation. And then we get another point for actually doing a trapezoidal sum to approximate that value. Okay? And note that we're doing absolute value. So my values of velocity here, in fact, I don't know why I circled this stuff at the bottom, my acceleration. My values of velocity here, some of them are negative. But when I do my trapezoidal sum, I'm going to make those positive values because we're doing the absolute value of the velocity. So our trapezoidal sum should look like the first velocity, or the absolute value of the first velocity, plus the absolute value of the next velocity. That's going to be 14 plus 10, right? Because we have negative 14 and negative 10, divided by 2, and then multiply it by the width of that interval, the time length, that's 5, from 30 to 35. Then the next one we'll do 10 plus 0, because the next velocity is 0. And then that one, when we divide by 2, we're going to multiply by 15, because that's the time interval from 35 to 50. And then the last one will be 0 plus 10 divided by 2, because that's our last interval there, our last set of velocities. And 60 minus 50 is 10. And so this should be an approximate value for the integral from 30 to 60 of the absolute value of v of t dt. And if we just do the arithmetic on this, let's see here. What do we get? We get 14 plus 10 is 24, and 24 divided by 2 is 12. 12 times 5 is 60. And then the next one is 5 times 15, which is going to be 75. And then the last one there is going to be 5 times 10, which is going to be 50. So we got 125 plus 60, which is 185 feet. And you get 1 point for that answer. In part B, it says, using appropriate units, explain the meaning of the integral from 0 to 30 of a of t in terms of the car's motion, and then find the exact value of that integral. Right? And so in order to do that, what we're going to do is, well, first we'll explain what it is. So from 0 to 30, that is, the acceleration is how we measure the rate of change of the velocity. So in order to find what that is, when we integrate a rate of something, we get the amount of that thing. So what this is it's the total change in the velocity, right? So it's the 0 to 30, the integral from 0 to 30 of a of t dt. It's an integral of the rate of change of the velocity, so it's just the change in the car's velocity on, and we'll say in because it says using appropriate units, in feet per second on t equals 0 to t equals 30 seconds. And so now we want to find the exact value. Well, that should be really straightforward because we know the integral of acceleration is velocity. So it might be a little daunting at first when you read it to say, how am I going to find the exact value of this? Well, the integral of acceleration is velocity, so just evaluate velocity at 30 and velocity at 0, because that's how a definite integral works. Evaluate at the upper and the lower limits and find the difference. So v of 30 was negative 14, and v of 0 was negative 20. So negative 14 minus negative 20 is 6, and our units here are feet per second. And they gave you 2 points for this, 1 for the explanation and 1 down here for the correct value. In part C, it says, is there a time on 0 to 60 when the velocity must equal negative 5? Right? Well, we know that velocity is a continuous function. And if we look, we can see that there is a time at which the velocity is less than negative 5 and a time when the velocity is more than negative 5. So you can say yes, because v of t is continuous, the intermediate value theorem, and actually we should be good about this, we should write it out. The intermediate value theorem applies. And we'll note that we'll say v, and we can pick a lot of different values here. We'll just say v of 0 equals negative 20, and that's less than negative 5. And v of, we'll just say 60, because we are allowed to do the whole thing from 0 to 60. V of 60 is 10, and that's greater than negative 5. So v of t equals negative 5 on 0 to 60. because -5 is greater than -20, but less than 10. And that would get you 2 points here. 1 for the showing that -5 is between a couple of these values, and 1 for using intermediate value theorem with the initial condition that it was continuous. And in part D here, we are asking if there's a time when the acceleration must equal 0. And so for this one, as long as we can show, since we know that the acceleration is a continuous function and the velocity is a continuous function, we can say v of t is continuous and differentiable. And we know that it's differentiable because a of t is continuous, right? And a of t is going to be a continuous function. Therefore, it must have been, we must have had a differentiable function there. So if a of t is going to be continuous, and that means that we can use the mean value theorem. So the mean value theorem applies. And so the mean value theorem says that the average rate of change can equal the instantaneous rate of change. And so if I can find a place where the velocities are the same, then the acceleration must have been 0 somewhere. So what I can say is v of 25 minus v of 0 over 25 minus 0, well, that's equal to -20 minus -20 over 25, which is 0. So the average rate of change of the velocity must equal 0 somewhere between 0 and 25. So a of t, which is v prime of t, equals 0 on 0 to 25, which is on 0 to 60. And so we got 2 points there for that. 1 for saying yes because of the mean value theorem, and 1 for showing that v of 0 is equal to v of 25. And that's 8 points. And then the last 9th point was for having the correct units way back in parts A and B, where we were doing these explanations where it told us to use appropriate units. So as long as we had the appropriate units in both of them, that's our 9th point. And that is it for this motion FRQ, which was number 6 from the 2006 Form B AP Calculus AB exam. All right, this is question number 4 from the 2007 AP Calculus AB exam. It's a motion FRQ, and we're given a particle moving along the x-axis with its position at t, given by x of t is e to the negative t sine t, from 0 to 2 pi. And we want to find the time at which the particle is farthest to the left here. So in order to figure out when it's farthest to the left, we first need to figure out what its velocity function is, right? Because we can see when it's moving to the left and to the right and determine when it might be farthest to the left. So the velocity function we'll find by taking the derivative of the position function. And we'll have to use, of course, the product rule to do that. So the derivative of, the derivative of e to the negative t is negative e to the negative t, and we'll multiply that by sine t. And then we'll add to that e to the negative t times the derivative of sine t, which is cosine of t. And of course, it might be nice to factor out the e to the negative t from both of those, leaving you with a positive cosine t minus a sine of t. And so they actually gave you 2 points just for correctly getting that derivative. And then we want to know when this velocity is equal to 0.
because that'll allow us to figure out when the particle is moving left and when the particle is moving right. And we can't know when it's furthest to the left without knowing when it's moving left and moving right. So we'll set this equal to 0. And just setting it equal to 0 actually gets you a third point. And of course, e to the negative t is never equal to 0. But cosine of t minus sine t equals 0 if cosine of t is equal to the sine of t. And on the interval 0 to 2 pi, that happens twice, right? It's always at increments of pi over 4. And the first time that sine and cosine have the same sign is at pi over 4 in the first quadrant. In the second quadrant, sine and cosine have opposite signs. But in the third quadrant, they're both negative. So we're going to use the pi over 4 increment in the third quadrant, which is 5 pi over 4. And we don't have to worry about 7 pi over 4 because 7 pi over 4 is in the fourth quadrant when cosine is positive but sine is negative. So we have two places where this particle might be changing directions. And so what we'll do is we'll make a sign chart here that uses our endpoints, 0, and our two values of pi over 4 and 5 pi over 4 on it, as well as 2 pi here, to figure out, when this particle is moving to the left and when it's moving to the right. And that'll help us really narrow down our possibilities of when we're furthest to the left and furthest, or actually just furthest to the left, because it could be at any of these four right now. So if we plug in something between 0 and pi over 4, for example, let's say we were to plug in pi over 6 into our derivative here, or to our velocity, right? At pi over 6, v of t is equal to e to the negative t, right? E to the negative pi over 6, which is a positive number. And then the cosine of pi over 6, we know the cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is 1/2. And of course, root 3 is more than 1, so root 3 over 2 minus 1 is going to be positive. This ends up being a positive value, which means our particle is moving to the right because the velocity is positive here. If I test something between pi over 4 and 5 pi over 4, for example, pi, I can ignore the e to the negative t because that's always going to be positive. So at pi, v of t is just a positive number times the cosine of pi minus the sine of pi. Well, the cosine of pi is -1, and the sine of pi is 0. So we have a positive number times -1, which is a negative number. So now our particle moves to the left. And then at the end here, between 5 pi over 4 and 2 pi, let's say we pick something, we'll just say 7 pi over 4. We know that's between those. 7 pi over 4. Well, v of t, if we think about 7 pi over 4, again, e to the negative t is positive. The cosine of 7 pi over 4 is a positive value, but the sine of 7 pi over 4 is a negative value. So if I have a positive minus a negative, we're going to get a positive, so our velocity is again positive. So we can be furthest to the left when we stop moving to the left, right? Or when we first start moving to the right. So a possibility here is going to be 0 and 5 pi over 4. Those are our only two possibilities, because otherwise we're moving to the right, and we're not going to be the furthest to the left anytime we're in the middle of moving to the right. So pi over 4 and 2 pi don't make any sense. So we can just test our position now at 0 and at 5 pi over 4. So e to the, and in fact, we'll write this, x of 0 is equal to e to the 0 sine of 0, which is just 0. And x of 5 pi over 4 is equal to e to the negative 5 pi over 4 times the sine of 5 pi over 4. The sine of 5 pi over 4, well, we know that 5 pi over 4 is in the third quadrant, right? It's negative root 2 over 2. So this is negative root 2 over 2
times e to the negative 5 pi over 4, which is less than 0. And therefore, our particle is farthest to the left at 5 pi over 4. So quite a bit of work there to get that it's farthest to the left at 5 pi over 4. And in order to really get all the points, we're going to want to make a note here at pi over 4 and 2 pi, particle finishes moving right and cannot be farthest left because it's just been moving to the right. So that's going to be part of our justification here, why we eliminated pi over 4 and 2 pi as possibilities. So we ended up with 5 points here. We already talked about the first 3. The fourth point is for the answer, and the fifth point is for the justification, which includes all of this work showing that it's further left at 5 pi over 4 than it is at 0, and eliminating the pi over 4 and 2 pi possibilities. Or you could have just evaluated the position at pi over 4 and 2 pi and shown that they were bigger than this negative number that we got at 5 pi over 4, and that'd be fine too. In part B, it says find the value of the constant a for which x of t satisfies this equation that a x double prime of t plus x prime of t plus x of t is equal to 0. And so we've got, well, a times x double prime plus x prime plus x. So we've already found x prime, right? We already know that x prime was equal to e, we just did it in the last question, e to the negative t times the cosine of t minus the sine of t. So we've already got x prime, and we've already got x of t, but we still need to find x double prime of t. So that'll be the derivative of this, which will be e to the negative t times the derivative of cosine minus sine. Well, the derivative of cosine is negative sine, and the derivative of negative sine is negative cosine. And then we'll add to that the derivative of e to the negative t, which is negative e to the negative t, times our cosine t minus sine t. And so we could simplify that a little bit by just factoring out the e to the negative t. So if I factor out an e to the negative t, I'm left with negative sine t minus cosine t minus another cosine t, and because we have the minus sign here with the cosine t, and then plus a sine t because I have the minus sine t. So plus a sine of t, which simplifies further here. We end up with the sines will cancel out. We have negative 2 cosine t, so it's negative 2e to the negative t cosine t as x double prime. They actually do give you 2 points just for finding x double prime. Not 1 point, like I just said, 2 points. And then now we're going to plug in x double prime and x into this equation they gave us here, a x double prime plus x of t is equal to 0. So let's see what happens when we do that. We're going to have a times negative 2e to the negative t cosine t. And then we're going to have plus x prime, so plus e to the negative t times cosine t minus sine t. And then we're going to have plus x of t, which was plus e to the negative t sine of t, and we want that to equal 0. And they give you another point just for plugging that in. And so now we're going to just do our best here to simplify all of this out. We've got a times our negative 2e to the negative t cosine t here still.
And if I distribute this through, I get e to the negative t cosine t. And I get negative e to the negative t sine t. Well, that negative e to the negative sine t is going to cancel with this positive e to the negative t sine t. Right? So really, we're just now left with this is equal to 0. And they have, well, what do they have in common? They have an e to the negative t cosine t in common. So we'll factor out that e to the negative t cosine t, leaving us with a negative 2a plus 1 needs to equal 0. And we're looking for the value of a that makes this true. Well, we just need to set negative 2a plus 1 to be 0, which gives us a is equal to positive 1/2. And that is the fourth point there for part B in this motion FRQ, and that's the end of this motion FRQ. It was question number 4 from the 2007 AP Calculus AB exam. All right, this is question 2 from the 2007 Form B AP Calculus AB FRQs. It's a motion question. It's a calculator question. And we've got a particle moving along the x-axis. Its velocity is v of t equals the sine of t squared. They show us the graph, and they tell us that the position of the particle is given by a function x of t, and that at t equals 0, its position is 5. Part A just asks us to find the acceleration of the particle at t equals 3. So all we have to do here is just take the derivative of the velocity function at 3, right? So v prime of 3 is the acceleration at 3. And since this is a calculator question, you don't really have to do this by hand. You can just go into your graphing calculator, and you can hit math and go down to option number 8. Right? Option number 8 here is going to pull up a derivative for us. We'll do the derivative with respect to x of our function, which is the sine of t squared, so we'll just say x squared. And we want to find this value at x equals 3. So when we do that, we just get negative 5.467. And they gave you 1 point for doing that correctly. In part B, it wants us to find the total distance traveled by the particle from 0 to 3. Well, total distance traveled is always just an integral of speed, where speed is the absolute value of the velocity. So we just want to integrate the absolute value of the velocity, or the absolute value of the velocity, from 0 to 3. And again, since this is a calculator question, you can just go in and hit math. Option number 9, FNINT. And we'll just integrate from 0 to 3, the absolute value, which is math, and then the second column over, number 1, of our velocity function, which is the sine, again, of x squared. And we'll put our dx out here, and we get an answer of 1.702. And this time they gave you 2 points for this, 1 point for the correct setup, and 1 point for the answer. In part C, it wants us to find the position of the particle at t equals 3. Well, we can find displacement by integrating velocity. So we know that the particle is at 0 is at 5, right? So if we integrate from 0 to 3 the velocity function, that should tell us the displacement of the particle on the interval from 0 to 3, right? It tells us the position at 3 minus the position at 0. And if we just bring this x sub 0 to the other side, we get that the position at 3, which is what we're looking for, is equal to the initial position, x of 0, or I wrote x not, but x of 0,
plus that integral from 0 to 3 of v of t dt. And so we can just, again, use our calculator, right? X of 0 is 5, so we'll just do 5 plus the integral, so math and option number 9. That's way too far again. The integral from 0 to 3 of our velocity function once again, so the sine of x squared dx, and we end up getting 5.774 when we round that. And they gave you, let's see, they gave us 3 points there for that. 1 point for having the correct integral here, 1 point for using the initial condition, and 1 point for the final answer. In part D, it says on the interval from 0 to root 5 pi, find the time at which the particle is farthest to the right. Okay. So what we need to do is figure out when it's moving to the right. Anytime it finishes moving to the right, we should be able to have a local rightmost point. Right? So it stops moving to the right when the velocity goes from positive to negative. So that's going to be here, and then again here, and then again, of course, at root 5 pi, right? Because the velocity is positive when we're above the t-axis. So those are the 3 places where the velocity stops being positive. And so we can use our calculator to find those, or we can just set the original function equal to 0. And it doesn't really matter which way you do it. You know, if you do it on your calculator, you're just going to graph the function and find the x-intercepts. So maybe we'll do both ways, but if we set it equal to 0 itself, sine of t squared is equal to 0. Well, we know that sine is equal to 0 whenever we are at 0 or at pi or 2 pi or 3 pi. Right? So basically pi or 2 pi or 3 pi. Right? So if we're looking at these, here's pi, here's 2 pi, right? Here's going to be our 3 pi. Like these aren't actually pi, 2 pi, and 3 pi, but like those are the times when, you know, t squared is equal to these things. And so our different times will be at t is equal to root pi, root 2 pi, root 3 pi, root 4 pi, and root 5 pi. And of course, the only ones we want are the odd values. Right? This one's going to be root pi. This one is going to be root 3 pi, because the one in the middle here is root 2 pi. And then, of course, at the end, we've got root 5 pi. And so you can find them by hand, or you can go in and you can graph them on your graphing calculator. Y equals the sine of x squared. And we might as well change our window by hitting the window button up in the top left from 0 to the square root of 5 pi, because that's the interval that we're looking at. And so if you graph that, we get basically a compressed version of what the graph on the AP test showed you. And you can find those intercepts. We won't do all of them, but we can find them by hitting second trace. And then option 2 is 0. And just go to the left of one of the intercepts. Oh, that's way too far. Hit enter. And then scroll to the right of that same intercept. And this is going crazy here. Hit enter again, and then hit enter a third time, and it'll tell you 1.7724539. Right, so that's this one, 1.7724539. And you could find the decimal approximations of the other ones as well, but we'll just stick with the original values. And so in order to figure out its position at each of those times, well, we just need to do what we did in the previous part, right, where we did the initial position plus the integral from 0 to in this case, root pi of v of t. And then we'll also do 5 plus the integral from 0 to root 3 pi of v of t dt. And we'll also do 5 plus the integral from 0 to root 5 pi of v of t dt. And we can see that these oscillations are getting narrower and narrower. So it seems to make sense that it's going to be at root pi. But we need some proof of that here. So we'll plunge all of this in, and we're going to make our lives easy here. When we go out of here, we had this 5 plus the integral from 0 to, we wrote 3 of sine of x squared. We can just highlight that from up above and hit enter and just bring it back here so that now we can just change that 3 to a square root of pi. And when we hit enter, we'll get 5.895. So this one is 5.895. When we do the next one, I'm going to write these in a different color so things don't get kind of jumbled up here. When we do the next one, we can just do the same thing. Just go back up here, hit enter. And instead of root pi, we want root 3 pi. And that's going to give us 5.788. So we can already see that the value at root pi was more. And then we'll do the same thing here with the last one. Except instead of 3 pi, we're just going to use 5 pi. And it gives us 5.752. And we can see that the largest one is 5.895. So the particle is furthest right at t equals root pi. And they gave you 3 points here for part D. 1 for setting the function equal to 0. 1 for the correct answer, and 1 for the reasoning, which in our case is this work here showing the 3 possibilities and what we got there for each of them. And that is the end of this motion FRQ, question number 2 from the 2007 Form B AP Calculus AB exam. All right, this is question number 4 from the 2008 AP Calculus AB exam. It's a motion FRQ. We got a particle moving along the x-axis, and we're given a graph of its velocity, which is a differentiable function. And it tells us that at 0, 3, and 5, the velocity is 0. And then we have horizontal tangents to the velocity at 1 and 4. In other words, a local min or a local max at 1 and 4. And then it also gives us the area of the regions here bounded by the t-axis as 8, 3, and 2. So I'm going to just note each of those. That's 8, that's 3, and that is 2. So it's kind of like a little bit of a combo of a graph FRQ with a motion FRQ here. And we also know that at t equals 0, the particle has an initial position of x equals -2. So for 0 to 6, we want to find the time and the position of the particle when it is farthest to the left. Well, the particle starts at -2, and then it's moving left because our velocity is negative. How far did it move to the left? Well, its position at 3, x of 3, is just the initial position, -2, plus the integral from 0 to 3 of v. Well, the integral from 0 to 3 of v is going to be -8 because this is an area of 8 units below the t-axis. So it's -2 minus 8, which is just going to be -10. And then the other possibility, see, it moves to the right up here when the velocity is positive, so we know that it's not going to be anywhere on that interval because we're now 3 units further to the right. But it could be at the end at 6, so we'll find x of 6, and that should be the initial position, -2, plus the integral from 0 to 6 of v of t. Well, the integral from 0 to 6 is a -8 and a +3, and then a -2 because this area is below the x-axis. And that comes out to be -9. Well, since those are our only 2 possibilities, it must be furthest to the left at t equals 3 when it is at -10, right? Since -10 is less than -9. So we'll say farthest left at t equals 3 when x is -10. And it's always good to make a note that we knew that it was moving to the, we said moving left on 0 to 3, right on 3 to 5, and left on 5 to 6. And so we're checking only 3 and 6 as our 2 possibilities. So a little bit of justification there as to why we only checked 3 and 6, since it does say to justify your answer. And you got 3 points for this. 1 for just identifying that t equals 3 was a possibility. 1 for considering the integral from 0 to 6, so the endpoint. And then 1 for the conclusion here with a bit of justification up here. In part B, it asks us how many values of t when we're on the interval 0 to 6 is the particle at -8. Well, this is a particle that is moving continuously, right? So we can say that v is continuous. We know that, right? And it's a differentiable function. So if it's continuous, if the derivative is continuous, that must mean that the position was also going to be a continuous function. So we can say our position is continuous, and therefore we can apply the intermediate value theorem to find when the particle is at -8. We know it's at -2, which is greater than -8 at t equals 0. And then we knew that the particle is at -10 at t equals 3. And -10 is less than -8. So if we went from -2 to -10, that'd be once. We're going to say once between t equals 0 and t equals 3. And then if it's now at -10, and then at 5, we know that the particle, we'll say at t equals 5, the position, well, if we were at -10 and we added in an area of 3, we're going to say x is equal to -7, which is now greater than -8. So once, again, we had to pass through on 3 to 5. And then if we went all the way out to 6 at t equals 6, the position we already found earlier, we subtracted 2 more from that, was -9, which is now less than -8. And then we also had then once on 5 to 6, right? And so these are all by the intermediate value theorem. And so we can say that it must have been 3 times. And that is all you really need to do. Just state those positions, state that the position function is continuous, and use the intermediate value theorem. They gave you 3 points, 1 for having all these positions, 1 for describing that the position is continuous, because you can't use IDT without saying that, and 1 for the conclusion of 3 times. In part C, we want to know on the interval from 2 to 3 is the speed of the particle increasing or decreasing? Well, speed is the absolute value of the velocity, right? And so the speed, we can think about it in two ways. Like if we think about the speed, we're going to have something that looks like this, right, on the interval from 2 to 3. If we just took the absolute value of the portion from 2 to 3. And so if we look at that, we can just see that, well, it's pretty clear that the speed is decreasing. So we do need a better explanation than that, though. So we're going to say speed is decreasing, because that's obvious just by looking at it. Because, and we're going to say because v of t is less than 0 on 2 to 3, right? Because our velocity is below the t-axis. And the acceleration of t, the acceleration of the particle, is greater than 0 on 2 to 3, which we can see that because the slope here is clearly positive, right? The derivative of the velocity is a positive value. Or you could say something like the velocity is negative but increasing, right? That would also work, right? So opposite signs of velocity and acceleration, or that the velocity is negative but increasing, means the speed is decreasing. And they give you 1 point here for just this whole answer. Now in part D, we want to know during what time intervals, if any, is the acceleration of the particle negative? Well, the acceleration is negative, right? A of t is less than 0 if v of t is decreasing. And we were given some places where we had local minima and maxima. One of them was at 1. Another of them was at 4. And so we know that a of t is less than 0 on the intervals when the velocity is decreasing. Well, that'd be from t equals 0 to t equals 1, because the velocity is going down there. Then the velocity increases here, but then it decreases again from 4 to 6. So we'll say and t equals 4 to t equals 6. And that's really all you have to do for this. That's worth 2 points, 1 for the answer and 1 for the justification that v of t is decreasing on those intervals. So that's the end of this motion FRQ. It's question number 4 from the 2008 AP Calculus AB exam. All right, this is question number 1 from the 2009 AP Calculus AB exam. It's a motion question. And we've got Karen riding her bicycle along a straight road from home to school. Starting at home at t equals 0 minutes, and she gets to school 12 minutes later. We've got a graph that represents her velocity, and it's a piecewise function that we can see there. And so we want to find the acceleration of her bicycle at 7.5 minutes. Well, 7.5 would be right around here. And so her acceleration is just the derivative of velocity, which is the function that we have graphed. So the derivative of velocity is just going to be the slope of the velocity curve. In other words, we just need to find the slope of this piece here. Well, we can just do y2 minus y1. And we start at 0.3 and we finish at 0.2. So we'll do 0.2 minus 0.3 divided by 8 minus 7. Well, that's negative 0.1 over 1, so just negative 0.1. It asks for us to indicate units of measure. So this was in miles, and it was miles and minutes. So this will be miles per minute, or miles per minute squared. And we get 1 point for the value and 1 point for the units. In part B, it says, using correct units, explain the meaning of the integral from 0 to 12 of the absolute value of v of t dt, and then defined that value. So, first of all, what does this mean? Well, the integral of the absolute value, that's the integral of speed. And an integral of speed tells you a total distance traveled. So we'll say that the integral from 0 to 12 of the absolute value of v of t dt is the total distance that Karen rode her bike and it says using correct units, so we'll say in miles during those 12 minutes. And we'll say the 12 minutes from t equals 0 to t equals 12. And so that's what it means, and you get 1 point for the meaning here. And then you get 1 point for the value of it. So we can find the value of the integral from 0 to 12 of the absolute value of v of t dt just by finding all the areas. This first area here is going to be 1/2 of the base, which is 2, times the height, which is 0.2. So 1/2 of 2 times 0.2. And then we'll add to that. This next one is below the x-axis, or below the t-axis, but we're doing absolute value. And so it actually becomes a positive. So we just got another 1/2 of 2 times 0.2, right? Since it's the exact same size triangle as the previous one. And then the next one here, we've got this triangle here, which is going to be 1/2 of the base, which is 1, times the height, which is 3. And then we've got this rectangle, or sorry, it's not 3, it's 0.3. And then we've got that rectangle, which is 1 by 0.3, so that'll be 0.3. And then we've got this section here that's a trapezoid. So that'll be the first base of 0.3 plus the second base of 0.2 divided by 2 times the width there of 1. And then we've got this rectangle that is 3 by 0.2. And then lastly, we've got this last little triangle here. That should be 1/2 of the base of 1 times the height of 0.2. And that's just a whole bunch of arithmetic here for us to do. And so if we add all that up, looks like this is going to be 0.1 plus another 0.2 plus 0.2, which is going to be 0.4. And then that's going to be 0.7. That'll be 0.85. Then we're going to add another 0.25, so that's going to be 1.1. And this is going to make it 1.7, and this will make it 1.8. So looks like 1.8 miles was her total distance traveled to get to school, including a little section where she went backwards, which I think we're going to talk about here in part C. So in part C, they gave you a point here at the end just for getting that answer. So 2 points for part B. So shortly after leaving home, she realizes she left her calculus homework at home. And so she returns to go and get it. At what time does she turn around to go back home? Give a reason. Well, we can see that she went back home when her velocity changed from being positive up here to being negative down here. So that'd be at t equals 2. So she turns around at t equals 2 because velocity goes from positive to negative. And, we can kind of just imagine exactly what happened here. She was riding off to school. She forgot. She remembered. She came back. She was at home getting it. And then she rode back to school with a positive velocity. And so you got 2 points there, one for the answer of t equals 2, and one for the reason that v of t goes from positive to negative. And now here in part D, we've got Larry, who's also riding his bicycle along a straight road from home to school. Takes him 12 minutes as well. his velocity is this w of 2 function. We want to know who lives closer to the school, Karen or Larry. And so to figure out how close he is, we just need to integrate this w of t function from 0 to 12 for Larry. So this is a calculator question, so you don't have to bother doing that by hand. So we're going to do the integral from 0 to 12 of w of t dt. Now we could do it by hand, but I'm not going to because they give us the option to use a calculator here. So I'm going to do math option number 9. We'll do an integral from 0 to 12. And then w of t was, we're going to use alpha and x to give us a nice fraction out in front. It was pi over 15 times the sine of pi t over 12. So we'll just say pi x over 12. And so we can see that that Larry is 1.6 miles from the school. And Karen's, we just need the integral from 0 to 12 of Karen's velocity here to figure out her displacement on her trip. Well, we already found the integral, the absolute value of it. And so that was 1.8. But this section here that was 0.2 was negative. And so, well, we added it as if it was a positive. So we have to kind of get rid of that. We have to subtract the 0.2, but we have to subtract it twice because we treated it as if it was a positive previously, right? So really we're off by 0.4. So from the 1.8 we had before, it should be 1.4, right? This section here and this section here cancel each other out. And if we look back to our work here when we did that, that's these two sections, which were both 0.2. So if we ignore those two, right, then we end up with just 1.4. And so since Larry's was 1.6 and Karen's was 1.4, Karen lives closer to the school. Karen lives closer. And you end up getting 3 points here for part D. 1 for just setting up an integral of Larry's velocity, 1 for Larry's distance, and then 1 for her distance with the conclusion that she is closer. And that is the end of this motion FRQ number 1 from the 2009 AP Calculus AB exam. All right, this is question number 6 from the 2009 Form B AP Calculus AB exam. That's a motion question. We're given a chart of values for the velocity of a particle moving along the x-axis. We're in meters per second here for our velocity. And we know that the particle's position at t equals 0 is 7. We want to estimate the acceleration, in other words, the derivative of the velocity, at t equals 36. So the best way to do this, right, to find a of 36, which is v prime of 36, is to just find the average rate of change in the chart from 32 to 40, because that's the smallest interval that includes 36. So we'll do 7 minus negative 4, right? V of 40 minus V of 32 over 40 minus 32, which just gives us 11/8. And it says to indicate units of measure. So we were in meters per second, so this is meters per second squared. And we got 1 point for the answer here of 11/8. Okay? And we had to get the right units in A and in part B to get the units point. So we'll do part B and then make sure we get that point for having the units in both. Part B says, using correct units, explain the meaning of the integral from 20 to 40 in the context of this problem. And it looks like I've cut off part of the question. It said use a trapezoidal sum to, with 3 subintervals as indicated in the table to approximate the integral from 20 to 40 is what this was asking you to do, which apparently I missed that part. I didn't cut that part out into this. So first of all, that integral is just going to be the displacement or the change in the position of the particle. So the integral from 20 to 40 of v of t, an integral of velocity is always the displacement of the particle in this case, in meters, from t equals 20 seconds to t equals 40 seconds. And then we're going to approximate it using this trapezoidal sum, right? And so for our trapezoidal sum here, we're going from 20 to 43 subintervals. So our trapezoidal sum, we'll just do, since they're not equal subintervals, we'll do -10 plus -8 divided by 2. And then times the width from 20 to 25, which is 5. And then we'll do -8 plus -4, right? The next two y values divided by 2. And we'll multiply that by 32 minus 25, which is 7. And then we'll do the last one, which is 7 plus -4, -4 plus 7 divided by 2, times the width of that from 32 to 40, which is 8. And then we'll just go and do all of that arithmetic. -10 plus -8 is -18 over 2 is -9, plus 5 is times 5 is -45. -8 plus -4 is -12. Divide that by 2 to get -6. So times 7, that's -42. And then -4 plus 7 is 3. 3 times 8 is 24. And then divide that by 2. And that'd be plus 12. So -45 minus 30 is -75. And of course, our units here are meters because that's our displacement units. And so you got 3 points here for this. 1 for just having the correct meaning. What is this? And 2 for the actual approximation. And then, of course, remember we got 1 from having the right units in A and B. So we've already got 5 total points here from parts A and B. If we look here at part C, it asks us, does the particle change directions in any of the subintervals indicated by the data in the table? And if so, identify them and explain your reasoning. Well, it'll change directions when the velocity goes from positive to negative or from negative to positive. And if the function is continuous. And since it's a differentiable function, it's continuous. So v is continuous because it is differentiable. Right? We know it's continuous because it's differentiable. So if v of t goes from positive to negative, or the opposite, or we'll say or vice versa, then the particle changes directions. Right, so that's what has to happen. And so if we look in the chart, well, between 0 and 8, it went from a velocity of 3 to a velocity of 5. So it doesn't necessarily change. From 8 to 20, though, it goes from 5 to -10. So we can say this happens on 8 to 20. And then it's still negative on these two, still negative on these two, but negative to positive here on 32 to 40. So we'll say and 32 to 40. So those are the 2 places when the particle changes directions. And you get 2 points, 1 for your answer, 8 to 20 and 32 to 40, and 1 for the explanation is that it's going from positive to negative or negative to positive there. And here in part D, it says, suppose that the acceleration of the particle is positive from 0 to 8. And it says, explain why the position of the particle at t equals 8 must be greater than x equals 30. Well, if the acceleration of the particle is positive between 0 and 8, that means that it certainly never slowed down and went in the, if the acceleration was 8, it was certainly always going to be having a velocity that was greater than 3 on that interval, right? And it must have increased solely from 3 to 5. So x of 8, the position at 8, which would equal the initial position of 7 plus the integral from 0 to 8 of v of t dt, we know that the integral there is going to be 8. It's going to be, we're going to have 7 plus we're going to have a distance of 8 from 0 to 8. And we know that the velocity then, if our acceleration was positive, is going to be at a minimum of 3. So we can say that since it was always accelerating, we know that we went more than 3 meters each second on that interval from 0 to 8, because we went from 3 to 5 and the acceleration was always positive. So our value must be greater than, well, in this case, it must be greater than 24 plus 7, which is 31. And so if we must be greater than 31, then we must be greater than 30 as well, right? So this integral must have been greater than 30 when we added 7 to it, so it must have been greater than 31 in the end. And they gave you 2 points for that, and we probably should note that, which is 31, so that's greater than 30. We could probably add that little bit there at the end just to make it sync up with the number that they gave us. We know it was greater than 31, but if it was greater than 31, it was also greater than 30. And so we got a point here for our explanation. And they say you get a point for saying that v prime of t is a of t. We didn't really say that here. But we know that the derivative of velocity is acceleration, and I think this is just maybe an old question where they wouldn't maybe wanted you to show that. I don't think that would be necessary anymore since this is now quite a few years old. But we know that v prime of t is equal to a of t. So they did give a point for saying that. So we should probably say that, even though it's really doesn't really affect how we go about solving the problem. And that is it for question 6 here. It's a motion FRQ from the 2009 Form B AP Calculus AB exam.